Now, it is probably of interest to ask how far can you push this technology? The Department of Energy is constructing a new modern synchrotron light source at Brookhaven National Laboratory called NSLS-2, and one of the specifications of the performance of this light source is that it should demonstrate 1 nanometer resolution in X-ray microscopy. Now, I personally asked the question, is there any science that you can do with 1 nanometer resolution? The reason why I'm skeptical is because in order to gain information out of such a small volume requires an incident radiation dose that, in my opinion, would probably disturb or destroy anything that you would want to image. So I would be more conservative than go to 1 nanometer. But nevertheless, the question as to how do you get there or how you approach it is an exciting topic. And in fact, on Thursday, there will be 3 symposia at this meeting where there are 8 speakers listed on this transparency who are going to talk about progress and challenges in nanofocusing optics. And while I'm on this point, I'm thrilled to tell you that just last month there was a paper in Optics Express which shows the latest results from the Center for X-ray Optics in Berkeley, where one of the 5 microscopes, in fact the oldest microscope operating there, was used to test the latest zone plate, which has a finest line width of 12 nanometers, and which demonstrated that you can visualize with it lines and spaces just 12 nanometers apart. Now notice that this is a factor of 2 better than the zone plate that I showed you earlier that came from the same laboratory, which is now something like 7 or 8 years old. So making further progress at this point is really quite challenging. And even though I'm confident that the 10 nanometer barrier will be broken, going much beyond that is going to be really difficult. So looking at alternatives is probably a good thing. And the group at Argonne National Laboratory has been looking into alternative ways of getting to high-resolution diffractive optics. They call these multi-layer Lousy lenses because when you go to very fine spacing and you still want to maintain some thickness, you basically have a waveguide in each of these channels where you want the X-rays to go through. And if you just make a thick zone plate with very fine lines, which is shown on the left as the flat MLL, you find that that's not really right. And the middle image on the left-hand side, the ideal MLL, shows that you need to incline the zones so that you have effectively a specular reflection from the walls of these zones toward the focus. Now, the challenge of doing the microfabrication of these fanned out zones is such that progress has been not particularly swift. It is just an enormously difficult microfabrication process. But to make progress in that direction, what they have done was to effectively take the flat multi-layer lens and break it in half and tilt the top and bottom half so as to, on the average, approximate the right direction. And on the plots on the right show the performance of these 3 different approaches. And you find that if you want to go from an outermost zone width of 20 nanometers down to 5 nanometers, you can still improve the resolution, and the efficiency with which the zone plate focuses optics is still finite. But if you go below 5 nanometers, if you want to reach less than 5 nanometer resolution, only the ideal, very difficult to fabricate, fanned out zone plate is going to perform anywhere close to what you need to get to. Now, the Argonne group and more recently the Brookhaven group have started working on building such multi-layer Lousy lenses, and the performance is the best performance is still not as good as zone plates, except for the fact that at least in one dimension, these objects are very good for focusing hard X-rays, and they have demonstrated 16 nanometer resolution at 20 kilovolts and 17 nanometer resolution at 30 kilovolts in one dimension, which is still quite impressive, and there are plans to put these cross two of these are effectively cylindrical lenses, and by putting two cross cylindrical lenses one behind the other, two-dimensional focusing is to be expected. Now, for the rest of my lecture, I want to get rid of optics. And there is a session on that subject as well that is going to be also taking place on Thursday. This approach is something that was suggested many, many years ago by David Sayer. And he asked the question is, what is it that lenses do for us? If you have an object and you illuminate the object with a plane wave, what you get in the plane of the lens is the Fourier transform of the object's electron density. And what the lens does for you is to conveniently perform the inverse Fourier transform to form the image. Now, we all know that computers are really quite good at doing Fourier transforms backwards and forwards. Why do we need a lens? Well, the problem is that we do not have a good way of recording this diffracted amplitude. The only thing we can record is the diffracted intensity, which is the absolute value squared of this diffracted field. In recording the intensity, we have lost the phase, which is the famous phase problem that all crystallographers are familiar with. And so we don't have enough information just by having this recorded intensity to perform a reconstruction. You have to have some other prior knowledge about the object, and then you have to have a clever algorithm in order to reconstruct the phases and to get a reconstruction. And I was very glad to see that Rick Millane, who is one of the experts at phase retrieval, who became a fellow of the Optical Society this morning. The scheme that is probably most popular scheme along these lines is one that was pioneered by Jim Feenup, whom I saw at a distance this morning, and I think he may be in the audience. And more recently, Veit Elser and his group has gotten into the business. This form of prior knowledge that has been exploited is to embed the sample to be imaged in an empty background. And if you are convinced that the sample is only in a finite region of space, which is called the finite support, you have a constraint that you can use by demanding that everything be zero outside this finite support. And so the algorithm that you use is to impose the requirement that your diffraction pattern be the right intensity distribution that you recorded on your in your experiment, and the reconstruction should come out in such a way that it has all zeros outside the finite support. And if you go around this loop many times and you have the right data then you get a good reconstruction of the image.